So for today, we're going to solve the third question on back substitution, and then we will start a new topic on discovering other methods for solving or finding a solution of recurrence relations. So as the steps explained in last lecture is that on draft side, so here we have a draft, try to enumerate or find some of the few terms of an or tn. So starting from tn minus 1, tn minus 2, because this is back substitution. So we have the equation for tn. We need to find the equation of tn minus 1. We need to find the equation of tn minus 2, and etc. So the equation for tn minus 1 will be equal to, if this is n minus 1, then how to find tn on the other side? It will be tn subtracted by 1. So if this is n minus 1, then this is going to be equal to n minus 2. So the relation between these two is that the second one will be decremented by 1. And also see the power. If this is n, then we have the power n. If this is n minus 1, then the power will be also n minus 1. By observing this information, it will be easy for you to find tn minus 1 rather than going back and forth on the equation to find the corresponding value for each tn of the recurrence relation. So let us find tn minus 1. It's going to be equal to 3 tn minus 2 subtracted by 1 plus 2 to the power n minus 1, which is the same value for the subscript and for the power. Now for tn minus 2, it's equal to 3 tn minus 3 plus 2 to the power n minus 2. Now for tn minus 3, it's equal to 3 tn minus 4 plus 2 to the power n minus 3. And I think 3 terms are enough, okay, to find a general formula at step number k. So we will have here step number, and then we will do back substitution. So this is a step number 1. In step number 1, we have the equation for an, which is equal to 3. I'm using an by mistake and supposed to be equal to tn. So tn is equal to 3 tn minus 1 plus 2 to the power n. Now for step number 2, we will substitute for tn minus 1 by its corresponding equation, which is equal to this. So this is the equation for tn minus 1. Multiply it by 3 and then substitute it into the equation. So it's going to be equal to 3 multiplied by 3 is a 3 square tn minus 2 plus 3 times 2 to the power n, and don't forget to copy the remaining terms from the previous step. Now for step number 3, you multiply the equation. Let me show you on the screen. So you multiply the equation of tn minus 2, which is this one, by 3 square. So the answer will be 3 square multiplied by 3 will be 3 to the power 3 tn minus 3 plus 3 square multiplied by 2 to the power n minus 2. Again, copy the remaining terms from the previous step. It seems that there is a small mistake that I have done probably here. This should be n minus 1. So let us correct it. I will move this term a little bit to the right, and this should be equal to n minus 1. Also, I will move this term a little bit to the right, and we write n minus 1. So now this is our equation. Let's go for step number 4. For step number 4, we will have 3 to the power 3 multiplied by the equation of tn minus 3. So we will have 3 to the power 4 tn minus 4 plus 3 to the power 3 multiplied by 2 to the power n minus 3 plus 3 square times 2n minus 2 plus 3 times 2n minus 1 plus 2 to the power n. So by looking at each term, this is a 3 raised to power 3 and n minus 3. This is a 3 square, and this is n minus 2, and this is a 3 raised to power 1 n minus 1. So maybe we can add here, okay, let me use different color, okay, for emphasis. So here we could add 3 to the power 0, as well as we can write that this is minus 0, okay. Now at step number k, now we can guess what will be the equation at a step number k. If you just observe for each step, step number 1 is 3 raised to power 1, step number 2 raised to power 2, 3. So at step number k, this is going to be 3 raised to power k, as well as Tn will be n minus k. Now for the summation, this is step 4. So we have a summation. Inside we have a 3 raised to power something multiplied by 2n raised to power minus something. If we go from the end to the beginning of the summation, then the first power here, see 0, 1, 2, 3. So we can have a variable, we will call it k, start from 0, and this will go up to n minus k. Now what will be the last value for k? Again, by looking at the summation from the end, the last one, see, if this is step number 4, then the last one is 3, which is less by 1. So at step number k, then the last power will be k minus 1. For 3, what will be the power of a 3? Again, by observing the power of a 3 in each term. Here we have a 3 raised to power 0, a 3 raised to power 1, a 3 raised to power 2. So it is again increasing until it reaches k minus 1. So we can put that this is equal to 3k. Now we need to combine the constants inside the summation. And for any equation or constant not related to the summation, just simply take it outside as common or outside the summation. So this is equal to 3 raised to power k, Tn minus k plus this number or this equation, we can write it as this one, okay. I can write it as 2 to the power n multiplied 2 to the power minus k. This number, which is raised to power minus k, depends on k. 3 to the power k also depends on k, so I cannot take them outside. But 2 to the power n is not related to k, so we can take it outside the summation. So we will have 2 to the power n multiplied by the summation. K goes from 0 up to k minus 1. I will combine these together. 3 multiplied by 2 minus 1 raised to power k. And this is equal to 3k multiplied by Tn minus k plus 2 to the power n. Summation. K goes from 0 up to k minus 1. When we combine them together, 2 to the power minus 1 is half. So this is going to be 3 over 2 raised to power k. This is a geometric sequence or series. This equation is a geometric sequence and starts from 0. We will find the corresponding value for this summation as a closed form. So what is the closed form equation now for the last step? This is going to be equal to 3 raised to power k times Tn minus k plus 2 to the power n. Now this is a geometric sequence and it starts from 0 and it goes up to k minus 1. So the answer for this one will be 3 over 2 raised to power k minus 1 over 3 over 2 minus 1. Let us leave it as it is, and this sequence and this substitution will keep going until we reach the initial value. So until Tn minus k will reach the initial value, which is T1. So we have the initial value T1. It is not T0. So it is given that it is T1, not T0. So if it is T1, then these two numbers are equal if their subscripts are equal. So n minus k is equal to 1. That means that k is equal to n minus 1. We need to substitute for the value of k into the equation that we found in this step, because the answer in here is in terms of k, and we need to find it in terms of n minus 1. So we will substitute, and then we will say that Tn is equal to 3. Now the relationship between k, so it will be 3 raised to power n minus 1 multiplied by T1, because n minus k will reach the initial value, plus 2 to the power n, 2 to the power n multiplied by 3 over 2 n minus 1 minus 1 over 3 over 2 minus 1. After we do the simplification, this is equal to 3n minus 1. Since the initial value T1 is equal to 1, so we will leave T1 as 1, plus after you do the simplification, the answer will be equal to the power n plus 1 multiplied by 3 over 2 n minus 1 minus 1. Why we are having we are having 2 to the power n plus 1? If you subtract 3 over 2 minus 1, 3 over 2 is 1.5. So if you multiply, it will be half. So it will be 1 over 2. So 2 will be taking up, multiplied by 2. So it will be 2 with n will be 2 to the power n plus 1. And what remains in here is this equation. If you just do the substitution up to here, then this will be like a correct answer, and you don't need to do any further simplification. But for your curiosity, we would like to see what is the simplified term for Tn. So Tn will be equal to, after we do the simplification, it will be 5 multiplied by 3 raised to power n plus 1 plus 2 to the power n plus 1, and this will be the last simplified answer for the recurrence relation.